Hello class, so we continue our lesson on compression members. Let's look over to local stability failure. So local stability actually happens when the elements of a cross-section are so slender such that the local buckling occurs prior to the column failure, okay? So which means that the member is more susceptible to fail locally than globally. Okay, so the strength in the global buckling mode can no longer be achieved because your element has buckled already. So this is a picture of how localized buckling occurs. Okay, so this is actually a flange localized buckling. So if you want to look it on the section, so this is a sectional view of how this part here buckles. No? So there's a buckling a failure on the flange. Also the web can buckle, so it's just difficult to draw it here. So maybe we can simply assume that this may actually buckle this form, okay, such that your uh, part here constitute what you call a web buckling failure. So for a wide flange section, there are two types of failure. We have the flange uh, buckling and the web buckling. And these are both localized buckling failure. So I will be discussing to you a separate video on how these plate elements behaves in terms of buckling. And here we simply try to understand the general concept by looking into the different types of local instability. So there are two types of elements involved in local stability. So we have the stiffened and the unstiffened failure or elements. So the stiffened elements are those which are supported, no? At both ends, and the unstiffened elements are those which are not supported at both ends. Okay. So when you say not supported at both ends, it is only supported of one end. So the support is one end only. So here's an example of a supported element. Okay, shaded here. Also this one, because they are supported on both ends. This is an example of a stiffened element supported on both ends. This is also an example of a stiffened element supported on uh, both ends. Okay, so these are the ends that supports them. Okay, while those which are not supported in one end, so your support are only on a single portion. So this is only the portion of this element. Okay, portion of this element. So we look into this as two elements, separate elements. Okay, so the support is only two, one at each. Also this, the support is only one at each end, and this is also supported only at this end. Okay, so the type of local failure behavior depends on whether or not your element stiffened or not stiffened. And we have here the basis for your measurement of susceptibility to localized buckling. So lambda, which is actually the width to thickness ratio, is compared to your lambda r, which is the limit. Okay, so lambda r is the limit, while this is the actual. So comparing lambda greater than lambda r, therefore your conclusion is that your element is slender. And if we have a slender element, the axial strength is reduced, and therefore it's more critical in terms of local buckling or local stability. So I also have here the AISC slenderless limits, which you can find on your manual. And take a look at this table B4.1, wherein your lambda r is given by the formula, depends upon the case description of the element. Okay, and these are for the unstiffened. Okay, and for the stiffened, we have the continuation here for the uh, table B.4.1. So this is for the stiffened. Okay, so this lambda r here are the values, and they are the limiting values into which your local instability will be determined. Okay, so this is still on the stiffened continuation. Okay, so when we go to problem solving, lambda r here for compression members having local instability, this will be our basis for our limits. Of course, these limits here have been derived using plate stability analysis. So for the LRFD column formula with local plate buckling, you will notice that there's a very big similarity on the global buckling formula or the flexural buckling formula. And the only difference is the uh, factor Q, which stands for the shape factor, okay, that is multiplied on this formula. Okay, so remember our original formula has no Q on this exponent. No? Note that your lambda c square is Fy over Fe, and the lambda c squared is simply multiplied by Q, or this can actually be written as Q lambda c squared. Okay, so still KL over R is less than or equal to your C sub C, or your Fe is greater or equal to 0.44 QFY. Okay, so you can compare this or this as your basis for your inelastic buckling. and this is for your elastic bar. Now, what is Q? Q is the product of QS and QA. So QS and QA are the shape factor for the unstiffened and the stiffened part. Okay, take note that the S here stands for unstiffened. Okay, magkamali kayo. And the A there is for stiffened part. So note that the shape factor Q is always beside the yield stress. So is this a yield stress Fi over Fe is multiplied by Q. There's an E over Fy there, you multiply it by Q. If there's a 0.44 Fy there, you multiply it by Q. So note QS and QA are determined from the table B4.1 and B4.2, your AISC reference. Okay, so that's it for the local stability concept. We will continue on our last consideration for instability or stability, which is the torsional and flexural torsional backplane on our next video. I'll see you guys on the continuation of this lecture. Thank you very much.